Hello everyone. So now we're going to do lab 1. You need to log on to Canvas first. So when you log on to Canvas, this is the interface you're going to see. You're going to click on modules, and then you're going to go directly to the lab manual activity folder and click on the first one, electric field PDF file. So once you click on that, you're going to see, let me see if I should do this. You're going to see the file. So I'm going to bring up the file. So this is the activity that you should read before you take the quiz. So what is the goal, or what is the objective of doing this experiment? Basically, you're going to find out what is the electric field produced by a point charge, and what are the equal potential surfaces produced by a dipole. Okay, so you're going to learn in the lecture course that when you have a point charge, and that charge usually comes with two signs, either it carries a positive charge or it carries a negative charge. And so whenever you have a point charge, it's going to produce an electric field in its surrounding. Any electric field has this expression, which is when you have 2-point charge, they're going to interact with each other. They're going to exert force on one another. So we can measure electric field by using this equation, which is what we call the Coulomb's law. So you have the force between the two charges over the magnitude of a test charge. So then after you figure that in, then the equations for the electric field that is produced by a single charge can be expressed by equation 2, and K here is a constant, and the Q is the magnitude of the charge. It can be positive or it can be negative, and R is the location between the point charge and the field point. A field point meaning that when you use a sensor to measure the electric field at that point, and that is what we call the field point. Okay, so you can see that electric field is proportional to the magnitude of the charge, and it's also inversely proportional to the separation square. So also the charge does have a sign. So if this a positive charge, it's going to produce an electric field that's pointing outward. If the charge is negative, it's going to produce the electric field that is pointing inward. Okay, so that's a difference between a point charge, whether it's a positive or negative. The directions of the electric field will be different. And when you have an electric field that is produced by a point charge, that point charge can also set up equal, potential in its surrounding. And we define potential, and potential itself does not have a physical meaning. It is a potential difference that has a physical meaning. And the potential difference is defined as, this is a line integral when you integrate electric field along the path. ds is the path from point A to point B. So after you figure out, apply to the, when you figure out the potential difference between point and A, it can be summarized, it can be actually evaluated to be this after you evaluate equation 3 for point charge. Then the potential produced by point charge is the K, again, the same K as in equation 1, and then Q, which is the charge magnitude, and over R. So the potential difference, so the potential produced by a point charge is KQ over R, okay? And so again, Q, the charge, is positive, carries, it can either be a positive charge or a negative charge. So the difference between the electric field and the electric potential is that electric field is a vector, okay? So it does follow the vector, addition and subtraction. So you have to treat that as a vector. Now for potential, it is a scalar. So you can just add them algebraically. And so it does not have any direction. It's not directional. So this is potential is KQ over R. So see, and then so when you read through this, you'll find that electric field and potential, they are related to each other. How are they related to each other? Basically, electric field is the negative dV/dr. When you do the derivative of the potential with respect to the displacement, okay. And so what we found here is that the potential change is zero for any displacement perpendicular to the electric fields. In other words, electric field and the potential and the equal potential surfaces, they are perpendicular to each other. So when you move, when you have it, so in other words, when the charge, let me just do this. Let's say this is a positive charge that produces the electric field. We just mentioned that the electric field produced by single charges pointing radially outward. Let's say we just use this full direction to indicate that it's pointing radially outward. So this is the direction of the electric field, and this it is a vector. And that charge is going to set up equal potential surfaces. So let's say it can set up several equal potential surfaces. And every point, so that's the one that's closest to the charge, so it has a larger strength. And then you might have another equal potential surface that's a little bit farther away. So it's going to set up equal potential surfaces like the concentric circle around this charge, and spherical shell, if you will, in the three-dimensional case. And you can see that the electric field and the equal potential surfaces, they are perpendicular to each other. So when we mention that equal potential surfaces, we mean that the potential at any point on the same circle or the same spherical shell will have the same value. Let's say this one, if you were to use a voltmeter to measure the potential, let's say you measure it to be 1 volt, then when you and then so every point on this that have the same radius will measure the same value, which is 1 volt. And let's say if you if you were to measure the potential value at the smaller at the circle that has a smaller radius, because this being closer to the source, so you would expect that it has a larger value because it's closer to the source. So let's say it registers a 2V potential. So every point on the same circle have the will have the same value. Okay, so this is what we call equal potential surfaces, and this basically just means that the electric potential, the potential change is zero for any displacement perpendicular to the electric field. Okay, then so with a three-dimensional case, this is basically the way to describe the relate the electric field to the potential to the potential, which is minus gradient V. If you're not quite sure about this, that's fine. If you have not yet learned that in calculus, then you're going to get very familiar with this. But if you're not familiar with this, that's fine, because yeah. All right. So if you look at this, you'll see that this is when you have a pair of charge, which we call a dipole. Dipole comes with consists of a positive charge and a negative charge. So in this case, you have a positive charge here, you have a negative charge there. And remember, positive charge produces electric field that's pointing outward. Negative charge produces electric field that's pointing inward. So when you have a dipole arrangement like this, you can just follow the electric field line. So this one, let's say for this one is pointing outward, and then when it comes to let's say this line, because positive charge is attracted, opposite charge attract each other. So this positive charge will produce the electric field that will terminate at the negative charge. So you can see that the electric field get bent, and then this one, because this is negative charge, electric field produced by negative charge is pointing inward. So you can see that that's basically when you have a dipole, it's going to produce the electric field pattern like this. So you have instead of so you have there's a point outward, and then it gets bent, and then this one is like connecting from the positive to negative and so forth. But but regardless, the electric field and the equal potential surfaces, they are perpendicular to each other. So the dash line here indicate equal potential surfaces set up by the dipole. So this one is going to set up equal potential surfaces like this, and this negative charge is going to produce equal potential surfaces like like this. Okay. So the experiment for today, the experiment basically, if we were to do this in the lab on campus, then you will be given two power source, and it will be arranged like this. So this is the you will have you have the two electrodes, and then this power supply. The negative is going to produce in reference to the positive. So this is negative end, and this is positive end. So we're going to supply we're going to turn on the power supply and then maintain the potential difference between these two electrodes. So this is equivalent to having a negative charge here and a positive charge there, and then you're going to use a multimeter to measure either the potential or electric field. So for this arrangement, this is the one that is arranged to find the equal potential surfaces. So in other words, you want to find a point where on the same circle that has you want to find a point on the same circle that has the same reading, and then once you find a point that have the same reading, it will form a circle, and then you move on from the positive charge all the way to the negative charge. And so so this one is a probe, and this is a voltmeter. The COM here is connected to the negative side of the power supply as a reference. Now to find the electric field, remember electric field is the negative of gradient, dV/dr. So you want to find the greatest change. So so you still have these two electrodes. This is negative charge and this is positive charge, and then you have two free ends, and the COM here is a reference, and this one V of M, this one is the probe. So you're going to use this as a center, and then use this positive end to trace out this circle to see at what point that gives you the greatest change or the greatest reading on the voltmeter, and that point will then be the new circle, and then a new reference point, and you use that to find the next point that shows the greatest change, and then move from the positive to the negative. So if you were in the lab, this is basically what you would do: use this arrangement to map out the electric field potential, equal potential surfaces, and also to map out electric field. Okay, so and then you will find that from the positive to the negative, you'll find that we would just pick any arbitrary 3 points and then go from there. So you can you start off from this track, then you will find the electric field is pointing from is going from the positive to the negative, and we will have a middle one. And then again, you can see the directions of the electric field is from positive to negative. And then from this one, that's again, so we will pick 3 directions. One is roughly 45, and then this is a horizontal, and then one is below 45, and then trace out the electric field produced by the dipole. And then you're going to find the equal potential surfaces by finding the points where they have the same value. So the experiment itself is very easy. There's really no calculation for this particular experiment. And so the analysis basically is that, you will use to find the positive negative, and you can read this stuff, but because we're not going to do this in the lab, instead, what we're going to do is we're going to use an online simulation, online simulation to kind of simulate this experiment. So here I'm going to show you when you click on this, go back to your canvas, you'll find that click on module again. Let's see. All right. So and then scroll down here, you can see that in this folder, this folder, the lab instructions and recordings are additional files. So once this recording is finished, I will upload the recording to this subfolder, and then you can see that in this subfolder, there's what we call the Physics 212 Lab 1 online simulation instructions. You want to click on that. So after you click on that, this is what you're going to see. So this basically provides instructions about how to do the simulation using the online simulation resource available. So you should click on this, and this will take you to the to do the work. But before you do that, let me just give you some overview about how to use this. So this is a screenshot of the that online simulation simulator, and so this positive charge. So you can see that you have a positive charge. So the red one indicate the positive charge, and the negative and the blue one indicate negative charge. So you can place so you can when you do the experiment, you can just drag this to place wherever you want, maintaining some distance between between these two charges. So you have the one that's positive and one that's negative, and then the yellow indicator sensor. So you can once you place a charge on in the simulator, it's going to show the directions of the electric field. So you want to observe the directions of electric field for the positive charge and for negative charge. And on this, the electric field, you can check or uncheck depending just play with this, and it's going to show you the directions only, or it actually indicate more information. And there's if you want a grid or a non-grid, and all that stuff. Okay, so how to place a charge on this on this, you just drag the charge out of the toolbox. So when you do this experiment, if you can do a screenshot, use the snipping tool when you do this, just to show me, how you, how you play around this. That you should include that in your data analysis. All right. So this is let's see. So when you check this and check that, the voltage and the value, it just show the you can view the electric potential. So you can see that the green line here indicate the electric potential. Okay, and this is just an example. It shows that 2-point charge here and then 2 negative charge here, and then you produce the equal potential surfaces like this, and the red, the yellow dot indicate the sensor, so you can actually measure the potential, equal potential values. And let's see. All right, and so this, you can plot the equal potential line. So you can just play around this to find what point that has a value, and then map out the equal potential surfaces. Okay, so the simulation notes. So the charges assumed to be pinned whenever they are placed. So you can just drag the charge to whatever, and that is where the charge will be placed. And the electric field is displayed using an array of arrows affixed to a grid, and the brightness of the arrow indicate the magnitude of the field. The direction only option remove the brightness gradient from the electric field to allow the direction to be explored separately from this magnitude. This is just basically, just give you some ideas about, how to use this online simulation tool. The sensor can be used to detect the precise magnitude and directions of electric field at any location. And the electrostatic potential can be displayed using the voltage checkbox. The brighter the color, the larger the magnitude of the voltage, okay? And the positive voltage is red, the negative voltage is blue, and the black represents 0 voltage, right? So that just, some of the things about the this online simulation tool. So the thing that you want to do is that in place of the lab that we would have done if we were on campus, is this. Okay, so you want to run the simulation to answer the questions posted below, and when you run the simulation, you want to make sure that you take a few pictures so that, and then include that in your data analysis. So I know that you actually did the work, and I can give you, I can give you points, to, because you show that you did that. Okay. So you want to, first of all, create a single charge. So instead of using a dipole, you just want to just have a single charge, whether it's positive or negative, doesn't matter. Or maybe you should have one that's positive charge and one is negative charge. And then you want to predict the direction and size of the electric field before the sensor is placed. And then determine the relationship between distance, magnitude of the charge, and the strength of the electric field around a single charge. Okay. And then you want to create a charge configuration with shear charge of opposite sign, which is a dipole, a positive charge and a negative charge, and place some distance away apart. And then you want to predict how the electric field around the charges will look at 4 different points. So these are all, you have the freedom to choose what 4 different points that you want to describe, you want to answer the question. And determine where the electric field is greatest for 2 opposite charges in a line. Is there a point where the electric field is 0? Okay, so again, you want to go back to the lab packet that shows the positive charge and negative charge, and then look at the pattern, how the electric field is being produced by a dipole, and then that will help you answer this question. In addition to using the online simulation tool to validate or to help you visualize, the electric field produced by a dipole. And then you want to identify the factors that contribute to a large electric potential. Okay, so again, we're not going to have sample calculation for this particular lab. There's no graphing. You just need to take a few pictures of the online simulation when you did the online simulation. And the data, there's no data, for this particular, there's no data provided to you for this particular lab. You have to actually use the online simulation tool to do the experiment. And then once you, let's see, once you finish, once you watch this recording, read the lab packet, activity 1, and read this online simulation instructions, you should be ready to take the quiz. So click on the assignments. And so your first lab, electric field, the quiz will be available on August the 30th, the Sunday at 12 a.m. And it will be available on Sunday. In fact, the quiz, the data analysis, and the lab report, all this will be visible to you on August the 30th, Sunday. And then for lab quiz, it's due September 1st, it's due Tuesday, September 1st by 11 p.m. The analysis should be, you should submit, everyone in the group should submit their own, should submit the data analysis by September 3rd, by 11 p.m. You can collaborate together. You can have the same data analysis page. That's fine, because this is a group work. So but each one of you should submit the data analysis, because there's a sample calculation. There's no sample calculation for this particular lab, but for future labs, there might be sample calculations. There might be figure that you need to do, or you work together, but each person might present the data analysis a little bit different. So that's why I want each one of you to submit your own data analysis. And then after that, you should remember to submit your report, and it's due Sunday, the next Sunday of the experiment. So that will be September the 6th by 11 p.m. Okay. So that's basically what you're going to do. If you have a question, you can either post your question in a discussion. So I'm going to click on the discussion. There's a one that is there's a discussion here that's for lab 1. If you have any question, this is where this is any questions that you have pertaining to lab 1. You can just just post your questions here, or you can email me, but I would prefer you actually post it in discussions, because some other students might have the similar questions. And I think that is it, okay? So I'm going to stop the recording.